So that was ionic bonds, covalent bonds. In Lewis structures, molecular compounds are shown as neighboring atoms that are sharing electrons. Nobody's willing to lose electrons here, and so instead of transferring them, we're going to share them. I'm not willing to give up this thing, but I'm willing to share it with you, because then it's still partly mine. So, instruction to myself, use Lewis structures to show bonding in H2O and Cl2. Okay, I can do that. Well, let's think about water, H2O. So I'm just going to keep this a single color because I'm tired. How many valence electrons does hydrogen have? 1. How many electrons does hydrogen have? 1. Okay, so there's a hydrogen atom, and here's another hydrogen atom also with 1 electron. And then I'm going to stick the oxygen in the middle because it's going to be convenient for me. And how many valence electrons does this oxygen have? Group number 6. So there's 2, and here's 2, and there's 6. Okay? Oxygen wants to follow the octet rule. It wants to get 8 electrons. And so it's talking to this hydrogen, hey, give me your electron. And the hydrogen's like, no way, I'm not giving up my electron. It's the only one I've got. You give me one of your electrons because I want to look like helium, so give me an electron. And oxygen says, no, I won't. Nobody will give one up. So, then the teacher or your mom or whoever says, well, you have to share your toys, right? If you're not going to, give them, you got to share. So they're going to share. So oxygen is going to share an electron with hydrogen. Hydrogen is going to share an electron with oxygen. When you're sharing something, it kind of belongs to both of you, doesn't it? So when this hydrogen looks at what it has this electron that it's sharing with oxygen, and also the electron that oxygen is sharing with the hydrogen. So there's 2 electrons here, and so hydrogen looks at what he's got. I'll make this green. And hydrogen's like, cool, I've got 2 electrons. Well, the oxygen isn't done yet. The oxygen also can count these electrons, but then it has 2, 4, 6, 7. It's not quite at 8. So oxygen is going to find another hydrogen and share an electron with that other hydrogen. And the hydrogen is cool with that because the hydrogen looks at the shared electrons and is able to count those as belonging to him. And then the oxygen, I don't know, red, it'll look kind of Christmassy here. The oxygen counts all of these. 2, 4, 6, 8. It's all very friendly feeling, right? Oh, they got together and they shared and everybody was happy. The nice thing about Lewis theory is, for the most part, you can make everybody happy. I mean, when can you say that in everyday life, right? You can't please all the people all the time. You can please all the atoms all the time. So do you understand why oxygen likes this? Because it counts these shared electrons as, these are mine. And hydrogen says, yeah, but they're mine. Well, yeah, they're both of ours. They're mine and they're yours. So we both have what we want without losing something. So the octet rule. Let's look at chlorine. Well, how many valence electrons does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Is this chlorine going to give an electron to the other chlorine so that chlorine can have 8? No, because then he'll have 6 and he'll be worse off. That's not going to be cool. They're going to share. I'll share 1 electron with you, you share 1 with me, and then we each get to count the shared electron as belonging to us. So we each have 8 now. So shared electrons count for both atoms. These are covalent bonds between nonmetals. Metals say, nah, I don't want to share with you. You can just have them, right? And the nonmetal is fine with that. But when you get the two nonmetals together, nobody's willing to give them up, and so they fix it by sharing. Get this whole world in my head. So any questions about that? And then it says identify bonding pairs and lone pairs. Lone pairs are just a shorter way of saying non-bonding pairs. Maybe I'll use the highlighter for this. So bonding pairs are the electrons that are actually being shared. So that's a bonding pair. This is a bonding pair. Over here, that's a bonding pair. So those are the bonding pairs. Then there are also some electrons here that are not being shared. Maybe gray. Gray is kind of a lonely color, right? So, lone pairs. So on this chlorine, here's a pair of electrons, here's a pair of electrons, here's a pair of electrons. They're not being shared. They're just sitting there by themselves. Those are lone pairs, or non-bonding. They're not bonding. And this chlorine atom also has 3 non-bonding pairs of electrons. Over here, this oxygen has 2 non-bonding pairs. The hydrogens don't have any non-bonding pairs because they only had 1 electron and they're sharing that with the oxygen. We need to be able to count lone pairs and bonding pairs for a future thing we're going to do. Any questions? Two atoms can share more than 1 electron pair. So let's look at oxygen, which forms a double bond. So here's oxygen and here's oxygen, and we've already talked about this, that oxygen has 6 valence electrons, so we'll just shorten this up and go like that. So I got 2 oxygen atoms, and they're trying to get 8 electrons. Well, hey, let's share. Okay, we share that. Do they each have 8? No, they each have 7. So I don't have enough. I need to share some more. And so they're going to share another electron. Now they both have 8. Right? This oxygen has 2, 4, 6, 8. And the other oxygen has 2, 4, 6, 8. 2 bonding pairs, 2 non-bonding pairs, 8. Now that's kind of awkward looking. And so we typically would draw that with the 2 shared pairs as 2 lines together. Yeah, question? But if it helps you, go ahead and draw the dot at each end to remind yourself, oh yeah, that's a pair of electrons, shared pair of electrons. So that's a double bond. In nitrogen, we get a triple bond. So nitrogen, 2 nitrogens. Nitrogens have 5 valence electrons. We talked about that back with the magnesium nitride. So how can we get 2 nitrogen atoms to be happy just together? Well, they could share an electron here, and then they could share another electron with each other, and a third electron with each other. And now there are 6 shared electrons, and then each has 2 non-bonding pairs, or 2 non-bonding electrons. So we would draw that as the 2 element symbols with a triple line representing a triple bond, and then the lone pairs. Any questions? Yeah. Yes, they both have lone pairs. So these dots, those are the lone pairs, and the lines are the bonding pairs.
Well, I guess we'll ask like the sum of lone pairs
Well, we're going to look at just how many lone pairs are on an atom, and that's going to help us determine the shape of the molecule. So I think of my husband and myself as being like a triple bond because we have 6 children between us, right? So, we can use this model to predict whether things are stable or not. So let's look at water and H2O and H3O. And we already have done H2O, so I'm just going to do that really quick here instead of talking through it again. And then how could we make H3O? Well, we'd need another hydrogen, and it's got 1 electron. And so how are we going to get these guys together? Well, if hydrogen shares with oxygen, this wrong screen. This hydrogen's happy now, it's got 2 electrons. But what about this oxygen? 2, 4, 6, 8, 9. More is not better. That's 9 electrons. That's not going to work. H3O doesn't exist. It's unstable because there's no way for 3 oxygens and a hydrogen to get their electrons together and make everybody be okay. So it doesn't happen. There is something we could do to this, though, to make it better. We could make it into an ion, H3O+, take off an electron. Right? So if I remove that pesky little electron there, now I've got a charge on the whole thing. But are the people happy? Yeah. Here, this oxygen has 2, 4, 6, 8 electrons. Nice. Doesn't really care that much. Am I bonded to 2 hydrogens or 3 hydrogens? I've got 8. That's what I'm going for. Each of the hydrogens has 2. Yeah. Yeah. You can just remove an electron like that? Well, we're just representing something that's actually that would be happening. You can't actually put the 3 hydrogens and an oxygen together in the first place. But we do know that H3O+ exists, and so we can draw the Lewis structure for that, and we see from the Lewis model that we predict that this is stable, but that the H3O is not stable.
So for us to put the charge on the outside, that lets us know that
there's a missing electron.
Inside,
Mm-hmm.
but it's just like
Yeah.
on the charge.
And then H2O2. Is that going to be okay? Well, here's HOOH. We're going to go over more how do you put these things together. Just sort of demonstrating the model right now. So there I have Lewis structures for the atoms involved. There's 2 hydrogens and 2 oxygens. And so I could take, here's a little added bit that's not in the book. When I look at oxygen here, how many unpaired electrons does it have? 2. Oxygen likes to form 2 bonds. And we'll see it usually does that. It doesn't have to. Here it's got 3 bonds, that's possible, but it prefers 2. So it can take this unpaired electron, didn't mean to do that, and share with hydrogen. And this other oxygen can share an unpaired electron with hydrogen. And then the oxygens are like, hey, I've got an extra electron here that I need to share. Oh, I do too. Let's share with each other. That seems to fit the Lewis model. And hydrogen peroxide is a thing. It's a real molecule. It's stable, relatively speaking. Any questions? Let's make sure I didn't skip anything. No? Okay. So again, looking at reality, kind of like we did with the ionic compounds, covalent bonds are highly directional. Maybe let's just go back and look at this. So you see that the shared electrons between the oxygen and the hydrogen, those shared electrons have to be between those two atoms. We can't have them off somewhere else. They have to be in that particular direction. If we move them, then we're probably going to break the bond. So this results in covalent compounds making discrete molecules. Instead of an ionic compound where you just have this repeating pattern of alternating positive and negative ions that can just go on and on and on, any size. With a covalent compound, the bonds are specific between two atoms, and so you're going to make discrete molecules. So this H2, this hydrogen peroxide here, is this going to share electrons with anything else? No, because it's good. It's good now. We're done. This is a discrete molecule. Is water going to share electrons with something else and form a big lattice? Not with covalent bonds, no, because it's all satisfied. So it's this little self-contained unit. And there are some attractive forces between the individual units, but they're not covalent bonds. Covalent bonds are shared electrons between two atoms. So we observe that molecular compounds tend to have lower melting points, lower boiling points than ionic compounds. A lot of molecular compounds are liquids or even gases at room temperature. Or they're solids that you can melt quite easily without burning up your frying pan. Because each of these discrete molecules has some very weak attractions to the other molecules, not strong bonds like ionic bonds that are non-directional. Yes? No, the bonds being directional means the covalent bond, let's see. Well, yes and no. What is that, C3? No, C, why do they do C5? This is a sloppy Lewis structure for this molecule. This bond is just between these two atoms, not anywhere else. This bond is between these two atoms. Between this hydrogen and the hydrogen in a neighboring molecule, there's no chemical bond. Whereas when you have sodium chloride, you have plus, minus, minus. What's a bad plus? I shouldn't talk while I'm doing that. Well, I really need another row here. Harder than it looks, actually. So for this ion here, and here we're just looking at 2 dimensions, for this ion, it's attracted by ionic bonds to 4 different anions here. They're not, how to say it, I don't know. And this just goes on and on and on and on throughout the whole thing. And so in order to melt this, you have to break some of those bonds. In order to melt this or to boil it, I don't have to break any of these bonds. All I have to break is these weak forces of attraction between the molecules. Does that help? And we'll talk more about what those are later. Any other questions?